Hi, and welcome back to the Differential Equations lectures here on Educator.com. My name is Will Murray, and today we're studying partial differential equations. We're going to meet some of the most common partial differential equations today, and we're going to focus on the heat equation. We're going to look at boundary value problems and some of the associated conditions that are often given as part of a package with partial differential equations, and we're going to learn how to interpret each one of those conditions in terms of a physical setting. So let's get started. So remember, a partial differential equation is an equation that relates a function of two variables, which we're going to call u of x and t. X and t are the variables, and u is the function. And so a partial differential equation relates u with one or more of its partial derivatives. So we did a whole lecture reviewing partial derivatives. So I hope you're comfortable with partial derivatives by now. If you're not comfortable with partial derivatives, maybe go back and watch the previous lecture here in the Differential Equations lecture series. I've got a long review of partial derivatives. If that lecture isn't enough, then you might want to go back and watch the videos from the multivariable calculus where they really do partial derivatives in more detail. So the most common partial differential equations have the second partial derivative of u with respect to x, so u sub xx, and then that gets related to either the partial derivative with respect to t or the second partial derivative with respect to t. So we'll meet a couple of those common partial differential equations in just a moment. But let me tell you about a boundary value problem. A boundary value problem is a partial differential equation which comes together in a package with initial conditions and boundary conditions. Often the boundary conditions are zero. So let me show you what I mean by that. The initial condition is this first condition here. The idea there is that you've plugged in time is equal to 0. So that's why it's called the initial condition, is because it takes place at time 0. So we've plugged in t is equal to 0. And so we just get a function of x. So this would be given to you in the context of the problem. All of these equations would be given to you. The boundary conditions tells you what happens when x is equal to 0 or when x is equal to some extreme value, which we're usually going to call L. So we plugged in x equals 0 or x equals L, which is a constant. And the boundary conditions tells you what happens at different times at the edges of your interval, at 0 on one side and at L on the other. So these collectively are boundary conditions. And we'll see how those get interpreted physically. But the important thing to know right now is that L is a constant, and all of this initial condition and these boundary conditions, these would all be given to you in a package along with the partial differential equation. And the goal is to find a function u of xt that satisfies all of them. So we'll see how to solve that over the course of the next few lectures. In the meantime, I just want to study this initial condition and these boundary conditions a little more carefully and see how we interpret them physically. So let's introduce the most common partial differential equations. There's sort of three very common ones. They're known as the heat equation and the wave equation and Laplace's equation. Each one takes quite a long time to really study and solve. So you kind of end up studying these same equations over and over again. Once you learn each one, then you really have a good grip of partial differential equations. So the heat equation says u sub t, remember that's the partial derivative of u with respect to t, is equal to alpha squared times u sub xx. What that alpha squared is, it's a constant, and I'll say what that measures in just a moment. U sub xx is the second partial derivative of u with respect to x. And what this equation describes is a function u of xt, which tells you the temperature of a solid rod. Rod could be of different materials. It could be a metal rod. It could be a wooden rod. We often think of it as being a metal rod. And it tells you the temperature of a rod at position x at time t. And x here is the position along the rod, and we usually think of the left hand of the rod as being x equals 0. The right hand of the rod is x equals L. So the rod is L units long, and so we're trying to solve this, discover what happens for all positions x between 0 and L, and for all time t. And the idea is usually that you know the initial distribution of heat in the rod, and then gradually the heat diffuses throughout the rod and it cools down, and you're trying to find a description of what temperature each place along the rod is at each time. So that's the heat equation, very common partial differential equation, and that's the one we're actually going to study and solve in the next few lectures here. The wave equation is another very common one, and it looks very similar. UTT is equal to c squared times uxx, and again, the c is a constant. I forgot to mention back when we were talking about the heat equation that alpha squared is a constant, and it's a constant of thermal diffusivity, which means it's a constant that depends on the material in the rod. If the material in the rod conducts heat very easily, then you have a higher value for alpha squared. If the material in the rod conducts heat poorly, then you have a lower value for alpha squared. So this, let me interpret the wave equation for you. The idea of the wave equation is you have a string that's attached at two ends. So again, we have x going from 0 to L. And this string, what you do is you pluck it, and so it vibrates back and forth. And so the string vibrates back and forth as time goes by. And so what you have is the string has a particular position, particular amount of displacement, at any given time. So this displacement depends on where you are on the string and on what time it is. And then u of xt describes the displacement of a string from 0 at time t. Now that c squared, that constant, is a factor of how elastic the string is. Of course, if the string were some completely rigid object, if it were just a metal rod, then it wouldn't vibrate at all. If the string were something very, very elastic, like a rubber band, for example, it's going to vibrate a lot. And so that c squared is a measure of how elastic the material in your string is. The last equation that's very common when you study partial differential equations is Laplace's equation, which says that uxx plus utt is equal to 0. And this one comes up a lot in complex analysis. I'm not going to interpret that one physically for you because it's not one that we're going to be studying later. We're actually going to spend most of our time studying the heat equation later. But I just wanted to show you Laplace's equation because these really are sort of the big three partial differential equations that people study. The heat equation, the wave equation, and Laplace's equation. So let's see how the initial conditions and boundary conditions affect the physical situation here. So let's jump into some examples. The first example just says, give us a physical interpretation for each element of the boundary value problem associated with the heat equation. And then what we have here is a partial differential equation and then several boundary and initial conditions. So let me show you how to interpret each of these equations here. I told you that alpha squared is a constant that depends on how easily the material in the rod conducts heat. So it depends on the thermal diffusivity of the rod. Diffusivity. I have a couple extra letters in my word there. Diffusivity of the material in the rod. Just to give you an idea, if the material is very, very conductive, then you'll get a higher value there. For example, silver has alpha squared is equal to about 1.7, whereas if it's a material with lower conductivity, then you'll have a lower value of alpha. Iron, for example, doesn't conduct heat as readily as silver does, so iron has alpha squared is equal to 0.12. So you get different values of alpha depending on how conductive the material in your rod is. Now let's look at these other conditions, the initial conditions and the boundary conditions. So let me draw a rod here. And you want to think of x going from 0 on the left-hand side to L on the right-hand side. Now, u of x0, that means we've plugged in 0 for t times 0 is equal to f of x. So what that really tells you is the distribution of heat in the rod when we begin the experiment. So that's something that an experimenter, that a physicist or a scientist would have to go and measure physically before starting the experiment. So that's the initial temperature of the rod. U of 0t, that means we've plugged in x equals 0, which means we're looking at the left end of the rod here. What we're being told is that u of 0t is equal to 0 for all time. So that means the left end of the rod is being kept at temperature 0 for all time. So you want to think of that as the left end is being kept at temperature 0, so it's being artificially forced to stay at temperature 0, perhaps by being packed in ice. So no matter how much heat might travel to that left end of the rod, say from the middle of the rod, we're forcing the left end of the rod to stay at temperature 0. U of LT, that means we've plugged in x equals L, which corresponds to the right end of the rod. If that's also forced to stay at 0, that would mean that the right end of the rod is also packed in ice. So all of these conditions would have to be given to you at the beginning as part of a package which is known as a boundary value problem. Given all of these conditions, then you could start solving the partial differential equation, trying to match the initial conditions and the boundary value conditions. And we haven't learned how to do that. That's going to be the content of the next several lectures here on Educator.com. So at this point, we're just kind of learning how to interpret each one of these conditions, what they mean physically, and we'll learn how to solve them next time. So let me recap there. What we said was this ut is equal to alpha squared uxx. That's the partial differential equation, and the only thing that ever changes there is the alpha squared, and even that never changes very much because that's always a constant. It just depends on the material that your rod is made out of. The u of x0, that means you plugged in t is equal to 0, so that means you're looking at the initial temperature of the rod. Again, this would all be given to you. So f of x would be a function that the experimenter has determined by going through and measuring the initial temperature of the rod. And then u of 0t and u of lt, that means you've plugged in x equals 0 and x equals L, which means you're looking at the left-hand end of the rod and the right-hand end of the rod. And if we're keeping them equal to 0, that would suggest that we've artificially forced both ends to stay at 0, perhaps by submerging both ends of the rod in an ice bath, and so that's how we know that they're going to stay at temperature 0 for all time. So let's look at a different kind of boundary value problem, still a heat equation. In example 2, we're still looking at a heat equation, but we've been given slightly different conditions here, so let's see how to give a physical interpretation for each element of this boundary value problem. So we have u sub t is equal to 1/4 u sub xx. That's the same heat equation as before, except we've been given a specific value of alpha squared here. And that's a constant which measures how susceptible the material in the rod is to conducting heat. So that's a constant of thermal diffusivity. And I switched these around a little bit. The u of x0 means we've plugged in t is equal to 0. So that's the initial distribution of heat in the rod, or the initial temperature in the rod, distribution of heat in the rod. So this is something that an experimenter would have to go through and measure the temperature at each place along the rod and tell you, the mathematician, what the temperature is at each place, at each position x, and at each time, well, at time 0. And then here's the new element for this problem. Instead of u of 0t, we have u sub x of 0t. So how is that different? Well, what that means is that if u sub x of 0t is 0, it means we've plugged in x equals 0. So we're looking at the left end of the rod, and if u sub x is equal to 0, that means the rate of change in the x direction is 0, which means there's no change in the x direction. So this is telling us that there's no change in the x direction, so there is no heat flow, and this is at the left end of the rod, because x is equal to 0. No heat flow across the left end of the rod, which means we somehow prevented any heat from flowing in or out of the left end of the rod, which means we must have packed it in some kind of insulating material. So the left end is packed in insulation. Now I want to emphasize the distinction there. Before we had u of 0t was equal to 0, which meant the temperature was forced to be equal to 0. Now we have u sub x of 0t is equal to 0. That means the temperature flow, the rate of change of the temperature, is forced to be 0. So this is really effect of the u sub x being equal to 0. There's no change in temperature across the left end of the rod. Before, when we packed the left end in ice, there could be a lot of heat sort of flowing out into the ice bath. Here, we're saying that there is no heat flowing in or out, so we must be packing it in some kind of insulating material to prevent any change in temperature across the left end. Now, we've plugged in x equals 1 for this second condition. These are both boundary conditions because they tell us what's happening at the edges of the rod. Boundary conditions. And so, since we've plugged in x equals 1, that must mean L is equal to 1. We must be dealing with a rod of length 1. And since it's equal to 0, that means there's no heat flow across the right end of the rod. Across the right end. So that right end must also be packed in insulation. So what we're doing here is we're not actually solving the problem. We're not doing any math at this point. We're just learning how to interpret each of these elements of a boundary value problem that would all be given to us as part of actually solving a heat equation. So the beginning here, this was the PDE, and this is always the same except that that value of alpha squared might change. But it'll always be constant, and it's a constant reflecting the kind of material you have in your rod. Material that conducts heat more easily would have a higher value of alpha squared. Material that is less conductive of heat would have a lower value of alpha squared. Now, the difference from this problem to the previous one, from example 1, is that in the previous one there was just a u, and here we have a u sub x. And what that represents is that at the left end of the rod, x equals 0, and the right end of the rod, x equals 1, we've got no change in temperature across the boundary, which means that there's no heat flowing in or out across the boundary, which must mean that we have artificially prevented heat from flowing in or out, which means we must have packed it in some kind of insulating material. So that's how we ended up concluding from these boundary conditions that the left end and the right end must be packed in insulation. And finally, we have this initial condition here, which says that u of x comma 0 is equal to some function of x. That's telling you the initial distribution of heat throughout the rod. So that would be something that the experimenter has to go and measure before presenting all of these conditions together as a package called a boundary value problem. So in example 3, we're also going to give a physical interpretation for each element of the boundary value problem associated with the wave equation. So let's see how to interpret each one of these elements of the wave equation. UTT is equal to c squared uxx. That's just the partial differential equation for the wave equation. And the only thing that ever changes there is that c squared. C squared is always a constant, but it might be a different constant depending on what kind of material you have in your string. So remember, the wave equation measures the displacement of a vibrating string at time t and at position x. So x varies between 0 and L, and t goes from 0 to infinity, because we want to watch this string sort of oscillate infinitely. Now that c squared is the constant of elasticity. It tells you how elastic the material of your string is. In other words, if you're dealing with, for example, a wooden rod instead of a string, that's not going to be elastic at all. That's not going to vibrate up and down at all. If you're dealing with something more flexible, like a rubber band, that's something that's going to be very elastic, and so would have a much higher constant of elasticity. Now, u of x0, that means we've plugged in t is equal to 0. So that means we're looking at an initial condition here. An initial condition. And so that would measure the initial displacement of the string. Maybe if you've taken the string and you've stretched it up, you've plucked it and you're about to let it go, that f of x would tell you the position of the string at any given point at time is equal to 0. So that's what that u of x0 is. U of 0t means we've plugged in x equals 0, which means we're looking at the left end of the string. And if that's equal to 0, that means it's not displaced at all for all time, which means you pin down the left-hand end of the string. So left end fixed. I'll say you pin down the left end of the string, is pinned down. And then the same kind of thing here. We've plugged in x equals L into u of Lt, and we've been told that u of Lt is equal to 0. So that means the right-hand end of the string is also pinned down for all time. So what all these equations mean, the first one is just the PDE, which tells you the general behavior of a vibrating string, and the c squared is a constant of elasticity, which depends on the material of the string. Depends on the material of the string. Is it actually string? Is it guitar wire? Is it rubber band? Is it something completely rigid, like a wooden bar. So you'll get different constants of elasticity, but within the context of any one problem, that number will always be constant, so it'll stay fixed at c squared. Now, the other conditions here are essentially keeping track of everything you would need to know about in order to determine and predict the behavior of that string. U of x0 tells you the position of the string when you initially pluck it or when you measure it at time 0. So if you stretch it up and then let it go, when you stretch it up, measure the initial position of that string, and that would be f of x. So that's the initial condition. U of 0t and U of lt means you've plugged in x equals 0 and x equals L, and what it's telling you, since they're 0, is that you're keeping the left-hand end and the right-hand end pinned down for all time. So let's go ahead and look at some possible solutions to differential equations. So we're going to look at the possible solutions to the wave equation. UTT is equal to 9UXX. So what we're going to do here is look at each one of several different types of functions, and I'm going to calculate UTT for each one, and I'm going to calculate UXX for each one, and we're going to see if they work out. They're supposed to work out. We're being told to check that each one works out. So we'll see for each one of these functions. The first one is U of xt is equal to cosine x sine of 3t. So let's figure out U sub tt, and then we'll figure out U sub xx for each one of these functions. Now, cosine of x times sine of 3t, when you figure out U sub tt, that means that the cosine of x, we want to think of that as being constant. And so we'll just have cosine of x coming down. Now, sine of 3t, we're going to take two derivatives of that. So the first derivative of sine is cosine of 3t. And then we multiply on a 3 by the chain rule. That's the first derivative. And then the second derivative would be negative sine of 3t. And we multiply on another 3. So we end up getting negative 9 there. And so U sub tt would be negative 9 cosine x times sine of 3t. Now, U sub xx works just the other way around. Now we think of sine of 3t as a constant, so sine of 3t is just going to come down as a constant, but cosine x, we need to take the second derivative of that. Well, the first derivative of cosine x is negative sine x. The second derivative of cosine x is negative cosine x. So U sub xx is negative cosine x times sine of 3t. And if you compare these to each other, what we see is that U sub tt is exactly 9 times U sub xx. And so it satisfies the differential equation. So we've just checked that our first function there satisfies the partial differential equation. So let's go ahead and try that with the second function here. U sub xt is equal to cosine x cosine of 3t. So U sub tt is cosine x, because we think of that as just being a constant since we're taking the derivative with respect to t. Cosine of 3t, let me take two derivatives of that. The first derivative is negative sine of 3t multiplied by 3 by the chain rule. And the second derivative of sine, is cosine of 3t. But we still have that negative, and now we get another 3 popping out, so negative 9 cosine of 3t. So negative 9 cosine of x, cosine of 3t. Then on the other side, we're looking at U sub xx, so that cosine of 3t will just come down as a constant, since you think of t as being a constant. Now, derivative of cosine, well, the derivative of cosine is negative sine, and the derivative of that is negative cosine. So our second derivative is negative cosine x times cosine of 3t. And again, if you compare those two to each other, on the left we have 9 times what we have on the right. So U sub tt is indeed equal to 9 times u sub xx. Let's try that again with the third function here. U of xt is equal to e to the t times e to the x over 3. U sub tt means we think of x as a constant, and we take the second derivative of e to the t, which is just e to the t. And then the e to the x over 3 comes down as a constant, e to the x over 3. U sub xx means the e to the t comes down as a constant, and we take the second derivative of e to the x over 3. Well, the first derivative is e to the x over 3 times 1/3, and then the second derivative is e to the x over 3 multiplied by another third, so we get 1/9. So I'm going to put 1/9 e sub t times e to the x over 3. And again, we can see that the left-hand side is equal to 9 times the right-hand side. So if we compare those to each other, they definitely do satisfy the partial differential equation. E to the t times e to the x over 3 is 9 times 1/9 e to the t times e to the x over 3. Let's try that again with u sub xt. U of xt is equal to e to the 3t times e to the x. So u sub tt means e to the x is going to be a constant. E to the 3t, second derivative of that, first derivative is 3e to the 3t. Second derivative is 9e to the 3t. So we get 9e to the 3t times e to the x. Over on u sub xx, that means e to the 3t is a constant, and the second derivative of e to the x is just e to the x. And so, oops, I wrote a 3 here. It should have been a 9. So what we see comparing the left-hand side and the right-hand side, the left-hand side really is 9 times as big as the right-hand side. So looking back up at our differential equation, u sub tt is equal to 9 u sub xx. Finally, in our last one, we have u of xt is equal to sine 3t plus x. Let me calculate that one out a little more carefully. U sub t is equal to, the derivative of sine is cosine of 3t plus x times 3, the derivative of the inside, and then u sub tt is derivative of cosine is negative sine of 3t plus x. Now we get another 3 popping out, so 3 times that first 3 would be 9. Now let's look at u sub x. U sub x is cosine of 3t plus x, and u sub xx is just negative sine of 3t plus x. We don't have to worry about the chain rule here because the derivative of the inside stuff with respect to x is just 1. So my u sub tt is negative 9 sine of 3t plus x. Just copying that over from the left there. My u sub xx is negative sine of 3t plus x. Now, if you compare these two to each other, you see again that the left-hand side is 9 times as big as the right-hand side. And so, again, we have a solution to the partial differential equation. So in each case, we have u sub tt is equal to 9 times u sub xx. So all of these functions worked as solutions to the wave equation utt is equal to 9 u sub xx. So let me remind you how we did that. In each one of these functions, we worked out u sub t and u sub tt and u sub x and u sub xx. And then I just kind of listed what we got on each of those for each of those second partial derivatives over on the right here. The important thing to remember when you're taking these partial derivatives is that whatever variable you're differentiating with respect to, you want to hold the other variable constant. So, for example, when I took the derivative with respect to t, I hold the x part constant. So even if I have cosine of 3x or something like that, it just comes down as one big constant. So what I did was took the second derivative with respect to t, second derivative with respect to x, and I did that for each one of these functions, holding the other variable constant each time. and then I checked on each one that what I got on the left for u sub tt really was 9 times what I got on the right for u sub xx. And it worked out in every one, and so I can say that each one of these functions really is a solution to that wave equation. In example 5, we're going to check that each one of the following functions is a solution to the heat equation ut is equal to 4uxx. We're going to also determine which one also satisfies the boundary condition u of 0t is equal to 0. So let me first just work out ut and uxx for each one of these functions. So let's look at u sub t and u sub xx for each one of these functions. So for the first one, ut would be e to the x, because that's a big constant, times e to the 4t times the derivative of 4t, so that would be 4 e to the x, e to the 4t. U sub xx just means you're taking the second partial derivative with respect to x, which the second partial derivative of e to the x is just e to the x, and then e to the 4t comes down as a constant. And now if you compare both sides here, it does look like the left-hand side is 4 times as big as the right-hand side, so we do have a solution to our heat equation there, to our partial differential equation. In our second function here, we've got e to the x over 2 on the left and e to the t on the right. So u sub t is just the derivative of e to the t, because e to the x over 2 is a constant. So e to the t, derivative is just itself, so nothing really happened there. U sub xx, well, if you take one derivative here, we get 1/2 e to the x over 2. If you take a second derivative, you get 1/2 times 1/2, so 1/4 e to the x over 2. And then the e to the t just comes down as a constant, so we get 1/4 e to the x over 2 times e to the t. If you compare those to each other, you do see that the left-hand side is 4 times as big as the right-hand side. So again, we have a solution to our partial differential equation. For part C, if we do u sub t, well, it looks like the sine x comes down as a big constant. And then the derivative of e to the negative 4t is minus 4 e to the negative 4t. And then if we take the second derivative with respect to x, the e to the negative 4t is just going to be a constant. But sine x, the first derivative is cosine x. The second derivative is negative sine x. The derivative of cosine is negative sine x. And so we get negative sine x e to the negative 4t. And now we notice if we look at both sides there, the left-hand side is exactly 4 times the right-hand side. And so again, our u sub t is 4 times u sub xx, so we do have a solution to the partial differential equation. Now let's look at u of xt equal to cosine of x over 2 and e to the negative t. So our u sub t just has cosine of x over 2 coming down as a constant. E to the negative t, the derivative of that is negative e to the negative t. U of xx, the e to the negative t is going to come down as a constant. The derivative of cosine x over 2 is negative sine of x over 2. But then we have to multiply by 1/2 by the chain rule. And then the derivative of sine is cosine of x over 2. Multiply by 1/2 again by the chain rule, so we get negative 1/4. So we get negative 1/4 cosine of x over 2 times e to the negative t. And again, if you compare the left-hand side with the right-hand side, the left-hand side is exactly 4 times the right-hand side. And so again, we have a solution to the partial differential equation there. So let me recap what happened here. Each one of these functions, what we did was we tried it out in the partial differential equation. And the way we tried it out was just by calculating the t derivative, holding x constant, and then the second x derivative holding t constant. And so here are all the derivatives that we calculated on each side each time. And then for each one, we checked that the t derivative, the use of t, was exactly 4 times the use of xx. And it did work out every time. And so each one of those really was a solution to the partial differential equation that we were given. Now we're asked also to determine which one also satisfies the boundary condition u of 0t is equal to 0. So let me do that on the next slide. So the next slide is where we're going to try to satisfy the boundary condition u of 0t is equal to 0. Let me remind you of the 4 functions that we had here. Our first one was u of xt is equal to e to the x, e to the 4t. Our second one was u of xt is equal to e to the x over 2 times e to the t. Third one is u of xt is equal to sine x times e to the negative 4t. And our last one was u of xt is cosine of x over 2 times e to the negative t. Now for each one of those, we're going to plug in x equals 0. So let's try plugging in x equals 0 for each one of those. Here we get e to the 0 times e to the 4t, which is just, e to the 0 is 1, so it's e to the 4t. Here again we get e to the 0 times e to the t, which is just e to the t. Here we get sine of 0 times e to the negative 4t. Now sine of 0 is 0, so this just cancels away to 0. And finally, here we get cosine of 0 times e to the negative t. Now cosine of 0 is 1, so this is e to the negative t. And what we're looking for is one where u of 0t comes out to be 0. So clearly the first one fails, the second one fails, the third one works, and the fourth one fails. So that's our solution right there. That's the one that satisfies both the partial differential equation and the boundary condition x of 0t is equal to 0. So just to remind you what we did for each function there, we're plugging in x equals 0. So in each one of these, we're finding u of 0t, plugging in x equals 0, and simplifying it down. U of 0t, u of 0t. My u's are starting to look like y's. Let me clean up those u's there. There. And for one of those, the function simplified down to be equal to 0, which is what we were looking for. And so we're going to say that that one is the actual solution to both the differential equation and to the boundary condition at u of 0t is equal to 0. So that wraps up this lecture on partial differential equations, and in particular the heat equation. Let me remind you that we didn't actually learn how to solve the heat equation in this lecture. We're going to learn that in the next lecture, where we learn about Fourier series. So actually, I think that's 2 lectures from now where we're going to learn about Fourier series. The next lecture is going to be on separation of variables. So let me just remind you what we did in this lecture. We learned how to interpret all the different conditions that come packaged with a partial differential equation, and we learned what each one of them means physically. We didn't actually learn how to solve a partial differential equation, but I hope now that you're a little more comfortable with interpreting each one of those initial conditions and boundary conditions that you would receive as part of a boundary value problem along with a partial differential equation. So hopefully you can interpret each one of those, you know what each one of them means, and in the next few lectures we're going to learn about separation of variables, and we're going to learn about Fourier series, and we'll actually learn how to put all that together and solve the heat equation. So in the meantime, you have been watching Educator.com. These are the differential equations lectures, and my name is Will Murray. So we'll look forward to talking to you in the next lectures. In the meantime, thanks for watching. Bye-bye.